and we're going to talk about AI model for infrastructure monitoring 3. You have seen yesterday we have talked about 2 previous parts, and today we are going to talk about the physics informed deep learning for inverse problem monitoring, and then following that we will talk about the operator as well as sequence learning. And with that we will also talk about the applications of advanced AI techniques in infrastructure monitoring. So here mainly you will try to see, or you will look into that. We are mainly going to talk about the civil infrastructure. So as we know that civil infrastructure, our buildings, bridges, dams, they are or any other kind of critical infrastructure. It is the very foundation of the modern society. And if you look into that, these assets actually support our daily life. They do also kind of support the economic activity, public safety. So because of this, their safety, longevity as well as efficiency, which are very, very crucial, not just for the engineering excellence, but also for the societal well-being as well as the economic stability. So one of the very important or the most powerful tools we have to ensure that this is structural health monitoring or SHM is that it involves the continuous tracking, as I said, or assessing the condition of the infrastructure. So by doing so, we can prevent small issues or growing any kind of catastrophic failure. And importantly, SHM also enhances the resilience of the structure as well, especially during the extreme environments like earthquakes, floods, hurricanes. And how we can do that? We can do this by providing the real-time data, and supporting the proactive decision making, right? So now one of the important part is the regular monitoring, right? So you can see that we have talked about in the second paragraph that why the regular monitoring or the importance of the regular monitoring we are concerned about. So when we talk about the regular monitoring, it's not just helpful, it is extremely essential. Detecting the structural weakness, they can early, as I say, that they can early save lives, they can protect the property. Without it, hidden defects may develop unnoticed anomalies which can lead to the catastrophic failure. So by using the monitoring data, we can plan timely repairs, we can also plan the maintenance, which will help us to maintain the structural integrity for this kind of critical assets. So beyond the immediate safety, this monitoring also provides a valuable insight into how the infrastructure ages over the period of the time, and how the material which is being made by the infrastructure is degrading, and where the vulnerabilities may emerge. So you can see that with this insight, we can take the preventive measure to extend the lifespan of this kind of infrastructure. For example, if you think about, if you want to implement the reinforcement or the material upgrades in advance, we have to ensure that the structures remain the functional and they have to be reliable for decades, right? In essence, you will see that proper maintenance guided by some kind of robust monitoring, they becomes a very important form of risk management in our infrastructure monitoring. And then, as we said, there are some, you see that we have also talked about the advances through the AI and predictive technologies. In the recent year, we have seen a dramatic advances in monitoring technology, particularly real-time data monitoring or real-time data analytics and collection and the analysis. So AI-powered systems, they can process the massive amounts of data from sensors embedded in the bridges, tunnels, pipelines. And by using this predictive maintenance or the predictive maintenance based on this data, they can represent a huge shift instead of just reacting to the problems after they suddenly just occur. So you will see that AI enables the forecasting of potential issues before they become very, very critical. This reduces the need of the reactive repairs, that also saves time, cost and energy. So if you will try to continue to see the importance of this monitoring civil structure, you can also see there is another important role of AI in the civil infrastructure when we talk about health monitoring. So as our infrastructure systems grow in complexity or scale, traditional methods of monitoring, they are no longer enough. So that's the reason manual inspection or simple threshold system cannot keep up with the volume as well as the complexity of the data which is being generated through this modern infrastructure. This is where this AI technologies, particularly machine learning or the neural networks and predictive analytics, they have become very, very important. And these tools, that they can enable us to effectively monitor and maintain the infrastructure, maintain the health of the structure, providing insights that were simply not possible before the decades ago. And this is where this kind of AI technologies, particularly as we said that the machine learning, predictive analysis, they play a very, very good role. So now if you will try to look into this few important parts. First, as we said, the machine learning or the neural network. So if you will try see this AI algorithms which allows to the system to learn from the historical data, and we have seen that in yesterday's lecture also, that what exactly neural network mean when we talk about CNN, ANN and different kind of other neural networks. So what this algorithm does is that they actually allow us to learn from the historical data. They improve their performance over the period of the time. So by identifying some kind of patterns or predicting the future conditions of this kind of infrastructure components, they actually help us to anticipate some problem before they actually occur. And you know that we have seen the neural networks, particularly when we talk about the neural network, they are excellent in recognizing complex or nonlinear relationships in data. And this capability actually makes them very invaluable for understanding the subtle pattern in vibration signals, or any kind of temperature shifts or any kind of stress levels, which traditional rule-based SHM where it does not work. Then we have also seen this term predictive analysis yesterday. So another powerful application of AI is predictive analysis, analytics, or you can say predictive analysis, by analyzing both the historical as well as the real-time data. By using this kind of predictive model, we can actually forecast the future events, we can anticipate the maintenance needs, and we can also prevent the potential failure throughout the period, right? And instead of just reacting to the damage after it happens, we can actually intervene those very, very early. And this is not only saves the cost, but also reduces the downtime. This can also increases the safety of this kind of infrastructure. And we will try to look into this predictive analytics. You can see that they are very essentially transform the maintenance from a reactive to a proactive discipline, and that's why it is very, very important. And then another important term in AI technologies is the data collection and analyzing of those data, right? So of course the quality of the AI-driven insight, they depend totally on the collecting the data, right? With the rise of the AI-driven sensors and the Internet of Things like IoT, we can gather a vast amount of data from structures like bridges, roads, tunnels, and any kind of other infrastructure assets. So this data actually includes, they can be structural vibrations, they can be temperature variation, they can be stress level, they can be several other things as well, right? So AI algorithm then analyzes to detect the pattern and the anomalies here. For example, they can identify any early signs of wear and tear, or they can also identify any early signs of stress points or other potential risks in the structure, often long before these issues actually become very, very visible with our naked eyes. So this approach actually allows for more precision maintenance, which ensures that the resources are used very, very efficiently and the risks are quite minimized, right? And then another important term is the visualization. So as we said that finally, that's one of the very, very important terms. Even the best data or the best algorithm are not always useful if the engineers or the decision makers cannot understand the results, cannot understand the prediction, right? So we have developed many advanced AI-powered visualization tools which can now convert the raw data into the intuitive formats, right? Like heat maps or 3D models or dashboards, right? They actually help us to quickly grasp the health of the infrastructure or to understand the prediction very, very easily, where it's sometimes difficult to understand from the raw data. And this empowers them to make the informed decision very, very rapidly. They also, especially during the emergency period, when we may not have too much time to understand the details, right? So you can see that AI is no longer a futuristic concept in the civil infrastructure anymore. It is already here. It is transforming how we manage and maintain the structure that supports our daily life, right? And from machine learning to the predictive analysis, we can see that through the IoT-enabled data and cutting-edge visualization tools, you can see that this kind of AI methods is making our infrastructure very, very safer, smarter, as well as more resilient throughout the period of the time. And now if we will talk about some of the opportunities or innovations, there are several opportunities. The first one is definitely the rise of AI in civil infrastructure, as we said. Over the past decades, AI technology, they have grown rapidly in popularity with many research efforts dedicated to automated solution in civil engineering problems. I think we have seen some of those papers yesterday also, that where the different kind of machine learning methods are being used in the civil engineering infrastructure. We have seen also the surges in study focusing on autonomous inspection or condition assessment in civil structures. And these advantages are this kind of advances in these methods. They have actually demonstrated the enormous potential of AI to revolutionize the way we monitor and we maintain any kind of critical aspects or the critical assets of this infrastructure. However, there are, as we said, there are very important secrets as well. While the research is promising, the adoption of these technologies has not kept pace with their development, right? Despite significant R&D efforts and any very high expectations of this model, AI-based monitoring systems have not yet evolved into a widely successful and reliable formula for intelligent infrastructure monitoring. And this gap between the innovation and implementation, they highlights an extremely major opportunity for us. It signals the need for breakthroughs and in how we translate the AI research into more practical, scalable solutions that work in the real-life infrastructure case. And definitely, as we said, that there are also some kind of challenges as well. The challenges or the major technical challenges, they could be the improving the accuracy and reliability of these AI models, which are being deployed in diverse environmental conditions, right, or ensuring the system can handle a massive data stream in a real-time condition, and also building the trust among the engineers or designers to ensure the adoption at different scales by using this kind of AI models. So those are, and then the gap between the R&D and the development. So using this kind of models between the researchers and engineers to the R&D and the development or more the real life structure, and that gap is also some way one of the limitations till now. So if you will see that, as we said, there are 3 stages of the AI development, and that framework helps us to understand where infrastructure monitoring could head us in the future. First one is definitely the first one, which is the artificial narrow intelligence. We also being called as an ANI, and this is the stage where most of our current AI systems sit today, and that they are highly specialized tools designed to assist human with some kind of specific task, say identifying some kind of cracks in a bridge or predicting some kind of stress point in the structure. So while they are very, very powerful, the systems still rely on human supervision and invention. So that's where this actually lies. And then another important one is the artificial general intelligence, and this has been called as an AGI. This is also the stage where most of our, the next stage after the ANI, the next stage of invention, where AI agent with human level intelligence, they're capable of performing a wide or variety ranges of tasks and functioning independently without human supervision compared to the ANI. In this context of this, or in this type of AGI, you can see that when we talk about the infrastructure monitoring, AGI would mean that AI systems actually that can autonomously inspect, they can autonomously diagnose and even recommend maintenance strategy without human oversight. And that's where the advantages come of this AGI compared to the ANI, that you need a very less amount of human supervision, you need a very less amount of human invention. And then another or final one, which is the artificial super intelligence, and that's been also called as an ASI. So this is the ultimate stage where AI systems become extremely intelligent than humans, right? And they can perform tasks beyond our capability. So while still hypothetical this method is, ASI still could transform the infrastructure monitoring into self-evolving. It can transform to self-improving ecosystem, so that they can handle the predictive maintenance and or emergency response and even resource location more efficiently than any human team could do. So you can see that there are 3 stages of this development. One is the ANI, which is being called as an artificial narrow intelligence. Second one is the artificial general intelligence, which is being called as an AGI. And the final one, where these models will work or perform better than the human brain or the human, that's been called as an artificial super intelligence, right? So defining the goal of the AI in our research is to still move from ANI to AGI, right? That's still our goal, and eventually to ASI. That's the current goal of as a researcher or as an engineer. That's the certain goal of us. So for fields like structural health monitoring of civil structure, this means that going beyond the narrowly focused tools to kind of develop truly autonomous and something very, very intelligent system that redefine how we safeguard our infrastructure, right? So now if you will try to continue the opportunities of the innovation in infrastructure monitoring, there are several transformative areas, and they can be like fully autonomous, autonomous inspection of robots, or they are Internet of Things, and and then multimodal learning and so on. So now if you will try to look into the first one, and that is the fully autonomous inspection of robots. So although AI powered inspection tools, they have advanced very significantly, and current system, they are still mostly operating in the realm of artificially narrow intelligence. That means still the first one, ANI, right? They are excellent at specific tasks. Definitely they are good at specific tasks like defect detection, segmentation, quantification, but they still rely, as we said, that heavily on human oversight, and they still rely on heavily on human invention or intervention. So complete automation where robots can do everything independently, it is still some distance away, right? And this gap actually presents a huge opportunity for the innovation, and this big leap actually is moving towards artificial general intelligence, that means towards AGI. And in robotic systems, especially if you will see that when we talk about robotic inspection system. So now you can imagine that we have an autonomous robotic inspector that actually behaves almost like a human inspector. That means they will be capable of exploring the environment, or inspecting and identifying the defects, right? Or collecting and interpreting the data, or maybe like making some kind of predictive or intelligent decisions about the best follow-up actions without any kind of human intervention. So or any kind of human input. So definitely achieving this would accelerate the autonomous process very high, dramatically improve their efficiency, and unlock the next level of autonomous inspection of civil infrastructure. And it represents a very bold but necessary step towards the fully autonomous monitoring system. And that's where the opportunity lies for us for the future development of this AI, right? And next one is definitely the Internet of Things, or the blockchain based age, intelligence of smart SHM. And this is another, or the second area of development, which is the IoT NML smart monitoring system. So in future you will see that in smart cities, we will see a vast deployment of these IoT systems, or the vast deployment of these IoT sensors in the infrastructures like bridge, road, tunnels, or even the buildings and many more. And what we try to will do is that we'll try to collect the real-time data on vibration, stress, temperature, and many other aspects which we are interested about, many other critical parameters. However, simply collecting the data, as we know, that is not enough. The true innovation lies in edge intelligence. That means processing the data locally. And then also you have to understand that the near the source using the AI assisted analytics, right? So by doing so, the systems can actually detect the structural defects in real-time effects, and they can reduce the latency, they can faster the process, safer the process before any risk actually accelerates. So blockchain technology can enhance this. They can actually enhance the ecosystem by ensuring the secure tamper-proof data exchange between the devices as well as the engineers. Thereby increasing the trust and reliability in the smart SHM system is very necessary. So that said, that current IoT-based sensing tools still face serious limitations. They have a lot of, especially when you talk about onboard computing capability. That's one of the the biggest disadvantages or limitations somehow right now in the IoT-based sensing tool. They're often unable to meet the performance as well as the reliability of the expectation of a fully autonomous intelligent SHM system. And this is the gap where highlights the clear research and the development priority for us to build a robust self-sufficient IoT sensor network with an integrated edge intelligence and security layer. You can see that there is a huge opportunity of the new research areas or new models to come into the picture, where we can get a self-sufficient IoT networks, and that will kind of help us to smart monitoring or real-life monitoring, right? And now if you will also see nowadays this AI-based infrastructure monitoring techniques, they are built on the complex algorithm. That means that demand significant amount of computer power, right? So this makes them very difficult to run on low cost. They can also resource a constrained edge devices commonly used in the field. This is also another gap. So you can see that in the future research, it's also there is a opportunity to develop some lightweight AI solutions that can operate efficiently in a very constrained environment and still deliver the reliable and the real-time responses. And this would actually help us to build some intelligent monitoring system which is more practical and widely used. So if you will look into the blockchain, they can actually help you in several ways in the system. They can actually enhance the efficiency. They can also enhance the scalability. They also improve the data security. They can improve the transparency, and they also enable the independent and decision making at the edge. So you can see that together, if you will try to combine this IoT as well as the blockchain based intelligence, we can actually transform how the SHM system collect, process the data, and further act on those data, right? So however, it is very important to also note that the research in this area are very early stage. People are still working on this, and we still need a lot of time to get some sustained attention from scientific community to reach it at fully potential level, right? So this is a very new area, and still there are a lot of opportunities to kind of work on this. And then there is another important opportunity, I would say, is that multimodal learning. So that's also a great the innovation. So currently most of these kind of vision based inspection techniques, they rely heavily on the traditional RGB cameras, and these cameras are attractive due to their low cost, and definitely they are immediately available. So that's the reason they're very good, but they have a lot of limitations. By projecting any kind of 3D object into a 2D space, you can see that RGB cameras often result some kind of information loss, right? Especially at a very, if your distance is quite a big, or if you have any kind of different scales. So, but their untapped potential here is that they are very cheap, right? And they can actually be used quite a lot. But if you see the structural health monitoring, you can see that as a community, we try to adopt multi-sensor fusion technique by combining the RGB with the depth of thermal as well as the hyperspectral data, right? Where we can achieve a much richer, much accurate understanding of the infrastructure. So now if you will try to approach or try to see this kind of approach and try to pair it with some kind of machine learning model like a deep learning model, that will actually allow the system to detect the defects, stress points or anomalies that might go otherwise unnoticed, right? So basically, if you will try to kind of use this image processing methods or multi-sensor fusion techniques with some kind of deep neural network or the deep learning method, you will see that you will be able to detect the defect quite fast. Even if you have a greater distance or a very different scales, you will be able to do that. And again, as we said that the combining the heterogeneous data sources, that can dramatically improve the detection accuracy, right? So in the context of civil infrastructure monitoring, that means that integrating the information from multiple type of sensors. That means it can be visual, it can be thermal, it can be hygrothermal, hyperspectral, or many more. And we try to kind of do that so that we can achieve a very richer and more reliable picture of the structural health, right? So however, you can see that despite of its potential, as we said, there are many other knowledge gaps as well. So which needs the more detailed investigation, which needs some more kind of experimentation. And one of the exciting development in this area is that the use of the augmented reality AR devices, such as like Microsoft HoloLens, which are now equipped with the multimodal sensors. You will see that. And these devices can actually support this AI-assisted multimodal inspections that will merge with the real-life visuals with some kind of digital analytics in the real life. So basically, you will see this is also a very kind of futuristic research. There are a lot of research should explore the ways to fully harness these technologies by using this multimodal data fusion with some kind of AR tools to understand or to revolutionize how we inspect or monitor the infrastructure, right? And then another important part is the synthetic data training. I think yesterday we have seen this in detail that AI-based monitoring approaches, they depend heavily on the large, high-quality training data sets, right, to produce some kind of accurate, reliable prediction. And unfortunately, when you will see the field monitoring data, they are often very limited. And the process of manually annotating it is like labor intensive, right, expensive, as well as a lot of time consuming. So this bottleneck significantly restricts the scalability as well as the adoption of the AI technique. And then another problem is the manual annotation introducing by the human error. That's another thing, right, which can actually adversely affect the model performance as well. So if you will try to kind of generate the data in a simulated environment, you can see that you can actually create vast amount of labeled examples for more quickly as well as the fraction of cost. So now if you remember the way we have talked about yesterday, the synthesizing the training data, do you remember that what are the methods we have talked about yesterday when we are talking about synthesizing the data by using some kind of AI tools? Anyone? In yesterday's lecture we have talked about it.
Pixel level image.
Yeah.
Bounding box.
Yes. So there are those kind of methods, right? The pixel level image, bounding box. Those are the way we kind of try to synthesize the data. And then also there are some kind of advanced methods like generative adversarial network, which is also being called as GIANs. GIANs also kind of allow us to create highly realistic synthetic data, right? Even when you have very automatic annotation, drastically reducing the time and the effort which involved in the preparing the data sets. This also enables training under some kind of diverse scenarios, or which can actually be any kind of extreme environmental conditions that are hard to capture in real life. Those are the PAs, when we kind of try to synthesize the data, and by if you will look into this, you can see that by embracing the synthetic training data, AI research community can actually overcome one of the biggest hurdles in the civil infrastructure monitoring and accelerate the development of the robust generalized models quite well. And as I said, that there are a lot of methods the way we can do that, and there is a certain ways we should follow that. So, which we discussed in the yesterday's lecture. So, please go back and try to look into that how important it is when we talk about synthesizing the data, and especially when we try to kind of get some practical data. We have also talked about the methods which have some practical relevance compared to just getting some data, right? And then there is another, cutting edge opportunities when we talk about the infrastructure monitoring, and that is the vision-based forecasting of the structural deterioration. So currently, you will see that most of the infrastructure or most of the infrastructure inspection schemes, they are schedule-based, right? Structures are inspected at a fixed intervals, regardless of their actual conditions. So this one-size-fits-all approach that can lead to some kind of inefficiency. Some structures may be over-inspected while others deteriorate unnoticed between the inspection period. Okay? So a key limitation here is the lack of accurate predictive models, and without this kind of models, you can see that infrastructure managers, they cannot transition to condition-based inspection, where inspection frequency adjusts dramatically, also dynamically according to the predicted deterioration level, right? So prevention or preventive maintenance is not new. By applying this AI-based forecasting to predict the deterioration from historical visual data is still an underexplored area. So there are recent advantages, as we said, the GIANs, which is the generative adversarial network. They are actually being used quite a lot. They have opened up exciting new possibilities to address these gaps. So what this GIAN done is that GIAN-based models, they can learn from the large volume of past inspection data to forecast future structural changes. That actually empower the infrastructure engineers to act proactively rather than reactively. That means before any damage occurs, they kind of go and take care of that, right? And this area is, as well as this is also very critical research frontier. It could revolutionize how we plan the monitoring system, how we plan the maintenance schedules and allocate the resources, right? And another important area or another area of the development or opportunities in the future infrastructure is that online super resolution of drone inspection video. That's another opportunity with the quality of the monitoring data. High quality data is very, very essential for accurate AI advanced detection. But in real world condition, as you can see that measurement noise is really unavailable, right? Even with the advanced sensors in drone assisted inspection also, video quality may suffer a lot due to the low cost of cameras, right? And also motion blur, they can also cause some kind of drone, due to the drone movement, that can also be another possibility. And then another possibility can be the distortion that could be introduced by some kind of fisheye lenses or something like that. And these are the factors that can actually severely affect the performance of the detection algorithm. And that's where the online super resolution comes into the picture. So this approach is actually enhances the resolution. They also enhance the clarity of the drone inspection video in real time by using some kind of advanced AI technique. So now you can see that there are a lot of those kind of techniques where you upload your video. If there is some kind of blur, some image is not clear, you can actually nowadays do that. And that's actually been called as an online super resolution or drone inspection video, or any kind of videos which you kind of capture it. So by cleaning and improving the video data on the fly, we can actually ensure that even the inexpensive or the imperfect hardware producers actually analyze the ready to footage. And this innovation actually would help to democrate the drone-based inspection as well, making them very both accurate as well as more widely available. And this is not only suitable for any kind of drone inspection video. This one you can also use it for any kind of images. You can take some, lot of images, and maybe some of the places the quality may not be correct, and depending on whatever the limitations are, you can use this kind of methods to understand or to actually increase the resolution of the videos or the figures you are interested about. And then, as we said that this is one of the very interesting or the biggest constraint of this kind of methods is when we talked about the unmanned aerial system, right, of the infrastructure where the physical inaccessibility is there. So that's the reason when we try to use this AI-based super resolution technique that come into the play. And these methods actually what they do is that they reconstruct the high resolution videos from the low resolution videos, especially they sharpening the visual data which is being captured, and they actually help us to cover the large areas without compromising the image quality or the video quality. They also operate more effectively without any limited flight time of their batteries. They also provide more reliable data for AI-driven defect identification and monitoring. So to fully exploit this opportunity in the SATM community, we kind of try to develop a very lightweight super resolution algorithm that can optimize especially for the drones, because drones we quite use a lot and that also have some kind of limited computational capacity. And but if you will see this kind of lab-based lightweight super resolution algorithm, they do have also there are some kind of resolution problem, there are some kind of computational efficiency. They may not be good with the big data, but they have been developed for very efficient first and capable of running in the real time, especially when you take the data from the drone. So real time you can analyze it, you can make the video better. But one of the problem, because this is a very newly developed technique, right? So they can struggle with the big data, and sometimes they can struggle if you're during the real monitoring system. But as I said, this is a very significantly new area, and there are a lot of research still going on in this area, especially when we talk about real-time monitoring. Here we are not just talking about uploading a video, uploading an image and getting a better quality, right? Here we are talking about that continuous real-time monitoring is happening, right, through the IoT sensor or through any kind of satellites or even drones. You are getting those images, getting those videos in the real time, and immediately kind of trying to make it a better resolution, give it back to the system, and so that it goes through the analysis process, right? And this whole process is still kind of under development, and there are a lot of research are still going on to get some online super resolution algorithm which can bridge a very critical gap between where the drones can safely capture and where as an engineer we can understand how this actually works out. And it has to be also very super performance, very kind of computationally efficient, and should be able to kind of perform in real time, should be able to deal with the large sets of data, and that's one of the very, very important points, right? And then if you will try to look into one of the most fundamental concepts in modern machine learning techniques is that automatic feature extraction from raw data, right? And why feature extraction actually important? So when we collect the data from the sensor, cameras or drones or any way, right, it often comes in a very raw unstructured form, which while rich in information, they do have a lot of information, and the raw data can be overwhelming sometimes, and they can be redundant also, and sometimes very difficult to interpret directly, right? And there are feature extraction. They can actually help us to transform this raw data into a set of meaningful characteristics, as we see. And these new features, they can capture most important information by ignoring the or reducing the redundancy, and they also help the algorithm to work more effectively. They also help us the algorithm to work more efficiently, accurately during this period. So how generally this actually works? So if you think about this feature extraction methods or the feature extraction tools, they can include techniques like dimensional reduction, because they are trying to take the most meaningful data, right? Some way it's also helping you with the dimensional reduction method. They also kind of use it on the techniques like mathematical transformation or creating entirely new features from the existing data. So how it happens basically is that there is an original data, right, and then you can think about some kind of scattered points in the space, which is mathematically transformed into a new set of features, right? So now if you will try to kind of do something like that, before we process about how it could work. So yesterday we have talked about a lot of neural network, or different kind of neural network. Do you think that we can actually use any kind of neural networks to kind of continue that with the feature extraction? Have you heard about any feature extraction methods or tools? So what exactly feature extraction does is that they are dimensionally they are reducing, right? They are mathematically transforming as well, and they are also creating entirely sometimes new information from the existing data. So what could be the methods where we could possibly use this?
We can use the GIAN.
Why?
If we have tabular data, we can, because in GIAN there is the activation functions. So when we choose the activation function, sometimes depending upon what we get the output. Suppose if we want from some tabular data, if we want to some combination of some non-linear data output. So we using the activation function like 10H or something.
Yeah.
So we can convert that normal data into some non-linear data.
So you get some more information from the this one,
Yeah.
but can we reduce the dimensionality and those things using the NL? You can do that as well, correct. So there are a lot of tools as well as a neural net. If you will see, not only ANN, there are also other kind of neural networks where some of these things we can actually do that. So basically, what happens if you have some kind of original data or any kind of scattered plots in the points in the space, we will kind of try to particularly look into this figure here, right? And you can actually mathematically transform into a new sets of feature. And this feature actually represents the core patterns of the structure, which is hidden in the original data. So basically, this has been hidden in the original data, and you are kind of trying to mathematically transform this data such a way that you are getting a core pattern which was not previously visible in the original data. And that's where it generally does, right? So by focusing on the most relevant aspects, what they also do is that this kind of feature extraction actually reduces the complexity. So now if you look into this one and this one, you can see that this is much more easy to calculate or easy to continue compared to this one. And they also improve the performance of the downstream machine learning model. And that's where it actually works. So in other words, you can say that the feature extraction does not just compress the data, they also reveal the insight of the data, what is there in the inside, might not be immediately apparent from the raw data, right? So there are a lot of practical benefits when we talk about the infrastructure monitoring. For infrastructure monitoring, especially when we talk about the automatic feature extraction techniques, they identify the subtle pattern in the stress, vibration or thermal data. They also reduce the noise, they also reduce the redundancy, from massive sensor data network also. And they allow these predictive models to focus on the most informative signals. And ultimately they improve the accuracy as well, and the speed of the defect detection and those things. So basically you can see that you have some kind of original data, and you transfer this original data into the extracted feature where you get some kind of information which may not be visible into this, and you are getting a certain data where now it is easy to analyze, easy to predict, and then definitely they are also kind of choosing some important or informative information or data compared to the whole sets of data, right? And that also kind of reduce the dimensionality, and then create new features, and those things they always come together into this. So now if you will talk about specifically that why it is important when we talk about machine learning, that why feature extraction matters in machine learning. Basically, feature extraction is not just a technical detail, it's a very critical step in machine learning. It can mean the difference between a model that succeeds and one that fails. Okay? When done well, if you will do it properly, you can see that using this kind of feature extraction method, they can actually give you a clear model, clear view of the data, helping it separate meaningful patterns from the noise. So similar way, you can quickly understand that if you have an original data, if you will not plot it properly, definitely you will miss some kind of important information, or maybe you are getting some information which is maybe not correct, because you cannot see those things in the original data, right? because you are seeing some of the information from the data which may be not correct if you do not select the model or the feature creation correctly. So that's the very important thing you need to kind of be considerate about. So you will see that there are lot of ways that we can actually do that, and then I have tried to kind of point down few. The first one is that enhancing the model accuracy and efficiency. So when working with the raw data or when you are working with the unprocessed data, you can see that machine learning models, they can often struggle to distinguish between what is useful information and what is irrelevant noise, right? That's some way machine learning always struggle with. So feature extraction is there to help on this. They kind of act as a data processing step that makes the machine learning model more effective, to make them understand that which one is the more useful information in the data. So if you, for example, if you have a model which is trained based on raw data, that might have 85% accuracy. The same model, if you will try to carefully train that by using some kind of extracted feature, you can see that could actually reach up to 95% accuracy, and without changing the model itself. So that's where we see that the importance of this extracted feature model compared to just using this machine learning model. And this improvement does not only come from tweaking the algorithm, right? It comes from giving the model a very better quality input data. So if you will try to use some kind of well extracted features, they kind of highlight the most important aspects of the data. They allow the model to learn very faster, they generalize very better, and they perform more accurately. So as we say that there are a lot of applications of this, detecting the defects or anomalies more reliably, operate more effectively, or basically you will see that this kind of feature extraction actually improves both the speed also. They can also improve the quality of the machine learning outcome, which is a huge advantage when we talk about dealing with massive sensor data sets, and especially during the case of infrastructure monitoring system. And then another one is that which is the managing a high dimensional data sets, right? Because we know that when we talk about the modern data sets, they often contain the hundreds or even like thousands or the lakhs of the features. While the wealth of the data can be valuable, it also have prevent some kind of challenging, like the cost of the dimensionality, as we say, which is being said as the point one. Basically, a number of the features grows, the data becomes very increasingly sparse, right, in the feature space, and this sparsity actually makes it very harder for machine learning model to identify the meaningful system or the meaningful patterns. And feature extraction is some way their work. So what is actually done is that feature extraction actually helps by creating a more impactful or more compact representation of this data, and that can preserve the essentially relationship while reducing the dimensionality. So you are actually kind of some way reducing your dimensionality also. And then another one is the high memory usage. So high memory usage is the high dimensional data. We all know that they kind of require more storage, right? They kind of require more computational power during the processing period. So by extracting only the most relevant features, we can significantly reduce the memory footprint of our data sets without sacrificing their information value, right? So that's where then we can kind of take care of the high memory use. And then another important one is that data visualization. So visualizing the data with more than 3 dimensions is virtually very impossible, right? So feature extraction actually allow us to reduce the dimensionality to 2 to 3 features, okay? And making it very possible or easy to plot and understand the structure of the data visually, right? So by reducing the dimensionality while you can see preserving the essential information, with the help of this feature extraction transformation like scrolling or high dimensional data into a very more compact data or very very kind of manageable form, so we can actually use this kind of feature extraction transformation. This will only not only improve the model efficiency but also will improve the model performance, and that actually gonna help us the machine learning model we are going to select that will learn faster and generalize better and produce much more reliable predictions. And then another important factor that why feature extraction is very important is that reducing the computational complexity. Especially we are talking, and you will see that all of these are always very interconnected. You cannot actually talk about those and ignore the other points. So all of these are very important and they are very interconnected. And you will understand that when we talk about the big data, when we talk about the IoT sensors or complex data, all of these points some way actually work together, and that's the reason we kind of need to use the feature extraction methods quite well, right? So as we said that the reducing the computation complexity, that's one of the benefits of the feature extraction, that how lower the computational requirement could be. So when we work with fewer and more meaningful features, training time become very, very faster. So models also use a very less memory during the development period. That means which is very, very crucial when we are scaling to the real world application. And so what we do with a very linear input space, prediction can be generated as well. Essentially what we do is less but the better quality data we get by using this kind of extraction method. And then also it prevents the overfitting as well. It improves the generalization. And another benefit is that better generalization. So basically using this kind of feature extraction, we can actually get that. Simple feature spaces, they can also, as we said, they prevent the overfitting, they improve the generalization, and if you reduce the complexity also, as we said, that means we can get actually more robust patterns, and we can see some kind of unseen situations which may not be possible, and that leads to some kind of improved performance of the new or advanced data, right? And that is the key requirement of the AI system when we try to use for the infrastructure modeling. That's the key demand where we talk about the real world conditions, right? Because real world conditions, they can always vary widely, right? So as we said that in the civil application, we want with more reliable prediction, faster processing, scalable deployment, and that's the reason we kind of quite interested about this feature extraction method. Now, if you will try to look into the automatic feature extraction, and and what could be the models of that. So one is that if you try to look into this one, so what visualization actually shows. So if you will see the left plot here, right, we see a model which is working directly with the raw data or high dimensional data here. So if you will try to notice this particular graph here, you can see that how the model tries to fit every small fluctuation, right? And this is a sign of complex, potentially overfit model. It's reacting to the noise rather than capturing the true underlying pattern. Okay. So now if you will try to compare with the right hand side, what is the difference you can see? Yes, correct, right? And how we have done this? We have done using the feature extraction method, right? So by using the feature extraction method, actually, the same data, if you will look into that, the same data can be actually transferred into the more cleaner, more simpler form, right? The model now finds a very clean, generalized pattern, which is clear to learn from and much more robust. So you can see that here, if you will not use this kind of feature extraction method, it may kind of catch some of the noise and may not be kind of giving you a correct model, and it can overfit as well, right? So side by side you can clearly see the comparison that how the feature extraction is so valuable. It's very, very important, and it reduces, as we said, reduces noise, simplifies complexity, reduces the overfit, and highlights what is exactly or what is truly important for us. So basically working with the extracted features, as we said that there are a lot of needs also, information needs we need to know. That means that we need that it can reduce the risk of overfitting, but it also leads to the better performance, right? And now if you will try to look into that, actually extract features from the raw data, there are two main approaches, the manual feature engineering and the automated feature extraction, right? So we will talk about each. So the first one is that the manual feature engineering. So how we do as a manual feature engineering? In the manual feature engineering, that totally relies on the domain expertise, right? That means using our understanding of the problem and the data to identify and create some kind of meaningful feature. So this is a very hands-on approach where the human analysis decides what characteristics of the data are most important in the model. So we need a lot of human invention in this, right? And in practice, this means that taking a raw data, right, applying into some kind of specialized technique to reveal the pattern, and that's how it is done. Maybe you can think about some kind of image processing, like manual feature engineering might include like edge detection we can use, or color histogram we can use, to capture the color distribution. We can use some kind of texture analysis to quantify the pattern, and shape description to characterize the object geometry, right? And these extracted features are then converted into the feature vectors, which is the machine learning model can understand and use for prediction. That's how it generally works. So now if you will see this particular figure here, so this figure is actually talking about the process below. As we said that we start with the original image, right? And then we apply the edge detection to highlight the boundaries, right? And then finally we convert into a feature vector. A sets of numerical descriptions like a density, that can be shape ratio, area, and this is a very structured representation, and that is allowing the model to learn from the meaningful information rather than just some kind of raw pixel. And that's how generally it works. So manual feature engineering is powerful because it definitely leverages a lot of human insight. It kind of takes the experience of the engineers when we know our domain very, very well, such as like identifying the tags, bridges and those things, So as being the experts, the engineers actually help us to encode the knowledge of the experts of the data they do have it over the period of the time before the model even begins to learn, right? So now as we said that for the tabular data, manual engineering or the manual feature engineering, they focus on creating new variables or transforming the existing one to make the data more meaningful so that the machine learning model can use it further, right? And that can be done in several steps. We can include creating interaction terms between the existing features. They can also include some kind of transforming variables using a logarithm or polynomial function, and then also encoding the categorical variables, like turning text to or categories into some kind of numbers the model can process. Basically, you have like red, green, blue, whatever models are, you just put it like 1, 2, 3, whatever, so that you put it like that, the machine learning model understand the language and they can deal with it, right? So now if you will try to look into the figure, you can see that the figure illustrates the process very, very beautifully. So on the left hand side, we have our raw data, right? The columns like age, income, city, it can be anything else also, right? So we're just giving one of the example. Similar way, you can see that how we have engineered the features and how we have transformed it. This is actually transformed into engineering features like age group or logarithm income and a more binary, is metro indicator. So this transformation enriches the dataset by adding context, by adding the meaning of your dataset to otherwise the plain number. So that the machine learning model, they can actually use this very wisely, right? And as I said that, when they are well done, these techniques actually enhance the quality of the data representations quite well, right? They allow the model to learn patterns more easily and significantly improve the model performance very, very well, right? On both the training as well as the unseen data. So basically you can see that this kind of manual feature engineering for tabular data is about combining the domain knowledge of the engineers with some kind of statistical transformation to create a very powerful informative feature so that the machine learning can learn from the data, right? And now another one is that, which is the automated feature extraction, right? So do we need to give some break, because we actually need to finish a lot of slides. Do you guys need some break or should we just continue? You just came now, that's why you don't need a break. Anybody else? Yeah, that's fine. Let's take some break. So we will start around just after 5 minutes. Okay? Start now. Yeah. Okay. So then, as we said that we have another one, which is the automated feature extraction method. And as we know that we have just seen unlike the manual methods, this automated feature extraction, they uses the algorithm to discover and create features without explicit human guidance, right? And this is especially very important or valuable for large or complex data, where with just small human knowledge, or sometimes it can create some kind of bias, some kind of variance. So this is a very good extraction method, where manual engineering very slow, they can be impractical also. We have like complex large data. So we automated approaches this model itself, they can identify the most important patterns and compress the data into a very new meaningful features. And there are one of the most widely used automated techniques are principal component analysis. This has been also been called as an PCA. So PCA actually transforms the data into a new set of uncorrelated variable, which has been called as an principal components. Each of the component captures the maximum possible variance which is left in the data, and that helps us understanding its underlying structure. And this method is particularly useful when we talk about the dimensional reduction, and it simplifies the data while preserving its very important information. We are not losing some important information, whereas we are also reducing the dimensionality of the data, and that's where it actually works. So in other words, we can say that PCA works, or the PCA takes the complex high dimension data and they turn into smaller number of meaningful dimension data, right? Which takes a for the machine learning model is very easy to analyze and all. So again, similar way, if you try to quickly look into this figure here, you can see that the original data points are scattered into 2 dimensions, right? And PCA identifies 2 new axes, one is PC1, another one is PC2, which represent the direction of the maximum variance, right? So by projecting the data onto this axis, we reduce the complexity by keeping the essential pattern intact, right? And this makes this also kind of makes the downstream machine learning model task very faster, because the model can understand the data very fast. They can process the data very fast, and accurately also we can do that, right? So as we said that the PCA or the principal component analysis is a very powerful automated feature extraction tool. And now we will try to move into the another one, which has been also called as an autoencoder. So autoencoder also somewhere types of neural network that has been designed to learn the compressed representation of the data. Unlike linear techniques like PCA, autoencoder captures the complex nonlinear technique. So when your data is nonlinear, when you have some kind of nonlinear relationship in your data, so autoencoder actually works beautifully there. They are especially effective, as we said, that in the high dimensional data sets, right? Where this kind of PCA method, they always kind of struggle with it. So in essence, you can see that autoencoders, they compress the input into a very smaller kind of bottleneck representation, and then it is deconstructed, forcing the network to learn for the most important underlying feature. And there are modern tools makes implementing these techniques for easier. Like there are a lot of tools like PyCaret or I think ACID. So those are actually being used quite a lot for this kind of methods. And they, if you will try to compare the manual as well as the automated approach, you will see that both of them are actually talking about making the model strength. But when you have to deal with more large models or more complex models, more nonlinear models, or when you want to kind of understand the details here, but both of these are actually reducing the your dimension or giving you, making the machine learning more easy to understand. But when you have a lot of non-linearity, especially when we talk about the practical case, then definitely we do use the autoencoder rather than the PCA. And then as we say that we have looked into two of these methods, and then the another one is that choosing which one is the best one. So as we said that the choice between the manual as well as the automated features, they depends on several factors, right? It depends on the complexity of the data, availability of the domain expertise, as well as the need of interpretability as well, and then also the computational resources and the time cost. Those are the main four factors which is very, very important when you choose whether you need to use the manual method or you need to use the automated method, right? Like if you try to look into very complex data sets under like a very tight time period, automated methods work best, right? And also there are a lot of human biases, or there are a lot of other manual issues could possibly happen. So automated actually works beautifully in that. But then you also have to understand that when you use the manual, you need some kind of domain expert, because we need a lot of human invention when we use that. So that's the period also some issues. And then there are certain methods or certain machine learning projects where you see that they use both, right? To blend both of the approaches like domain expertise as well as the automated method, and they blend it together and then use a very hybrid approach. And basically domain expertise, they guide the manual engineering of the features which is known to be important, and then what automated does is that they kind of step in to discover the hidden patterns or relationships that may not be obvious as a human expert. That's how this hybrid strategy or the hybrid model, they kind of understand and take the strength of both the methods, and that's how generally they can do that. So now we have discussed about why feature extraction is important and how they can be done manually, how they can be done automatically. So here you will look into some of the specific techniques across the types of data, because not all data is same. They can be image, they can be audio, they can be time series. Each requires their own optimized approximation or approaches. So the important one of the important one is the image process. We all know that for images there are feature extraction methods which focuses on identifying the shapes, identifying the texture, identifying the important visual cues. So then there are a lot of tools, I will say. One of those was SIFT, which is basically scale invariant feature transform. So yeah, so that's been used quite a lot. That actually helps you to capture the key points and the descriptions in images regardless of the scale or the rotation. And then another important one was HOG. So HOG is basically stand for histogram of oriented gradient. They actually emphasize on the edge direction or the texture, those kind of things. Right? They are very great at detecting some kind of objects. And then we know there are like CNN features. They are also very, very important, which is the convolutional neural network. They kind of automatically learn from the hierarchical features from the raw pixel, and they enable for the high accurately image processing, right? And then except the image processing, there can be several other kind of data which can be audio, right? So audio processing is also another kind of way that audio requires the features that capture pitch, that capture tone, the frequency. So for those kind of cases, there are a lot of methods like MFCC. So the full form of MFCC is mean frequency capsular coefficient. So they are widely used in speech, music recognition, or the model the human auditory system. And then another one is the spectral features. They describe how the energy is being distributed across the frequency. And then there is another one which is zero crossing rate, that measures that how frequently the signal actually changes the sign. So those are the cases where we kind of use this kind of methods. And then there is another kind of data could possibly be there, and that is basically the time series data, right? That's one of the important ones as well, because that gives a very interesting trends in time frequencies over the period of the time, right? The trends and the frequencies patterns over the period of the time. And we do a lot of the known one, which I think most of us have used, that Fourier transformation, right? We are used to convert the time domain into frequency domain to identify the domain application. I think anybody who works in the SHM area, I think we all have used the FFT, right, in that way. And then the statistical features, so they also kind of like mean, variance, skewness, they kind of provide a summary of the signals behavior, and that makes our model very, very easy. And another one is the wavelengths. So wavelengths also capture both the time as well as the frequency information very, very strategically and very, very simultaneously, which is very crucial when we think about non-stationary signals. So you will see that each of these domains, they kind of need some kind of specialized feature extraction method or specialized feature extraction technique to best represent its data. And according to the type of the data, there are different kind of methods we do use it, and by applying the right method to the right type of data, we can significantly improve how the machine learning model works and learn, generalize and perform. If you think about FFT, definitely we cannot use it for image processing, whereas similar way if you kind of try to use that histogram oriented gradient for the time series, it's definitely not work out well, right? So we need to understand which techniques to use it for each of the type of data. And then if you will try to kind of quickly look into the crucial steps in this one. So the first one is definitely the feature extraction of the image feature extraction. As we said that they transform the raw pixel data into the meaningful representation, and that actually help us to capture the essential visual information instead of just feeding the millions of unprocessed pixels into the model. And we extract the key features that describe the shapes, sizes, patterns, texture, those kind of things, right? And there are three main categorical of image processing or the image feature extraction method. One is the traditional method. So in the traditional method, what we do is that the methods like SIFT, which is the scale invariant feature transformation, or there is histogram of oriented gradient, and then there are ORB, and there are SURA. Those kind of help us to understand the key point. Those kind of methods help us to understand the gradient, the age descriptor, those things. And they are very, very fast. Definitely they are interpretable. They work well with the large data sets and not available, right? And then another kind of or another methods are the deep learning based methods. So deep learning based methods actually transform the feature extraction by learning complex representation directly from the data. So basically the methods like CNN, transfer learning, autoencoder. So those are the statistical methods are the different ones. So those are the methods we generally try to use that. So CNN feature actually kind of help us to automatically learn multi-layered features, right? Whereas if you think about the transfer learning, they actually allow us to train the network for new data, right? For new tasks. And we know that the autoencoder or the self-supervised, they kind of compress and extract the essential representation without the levels. Similar way, there is another method which is the statistical method. For the statistical method is basically this method use statistical properties of images to describe the pattern, right? And there are a lot of ways to do that. Color histogram, right? They kind of summarize the color distribution. Then there are textual analysis, right? They detect the repeating patterns. Then there is the age detection. They also kind of identify the boundaries. And then another one is the shape description. They actually kind of quantify the object geometry. So you will see that by actually kind of selecting the right mix of this technique, sometimes you kind of mix it together, sometimes you use it one at a time, like traditional, deep learning, statistical, whatever works best for your model. We can actually transform the raw image into compact, informative feature sets, right? And they can actually significant, as I said, that efficiency, accuracy, interpretability of our machine learning model, of our models or the computer vision models, right? And then if you will try to look into the another traditional computer-based methods, right? So there are a lot of traditional computer, as we said here, that there are a lot of ones like SIFT, HUG, SER, SURF, ORB. So now if you will try to look into few of those, you will see that what is exactly SIFT means. So SIFT is a robust and well-established method that detects the distinctive of local features in the image, right? It is very, very powerful because it identifies and describes the key points that remain stable under various conditions, right? In other words, you can say that it finds features that don't change much even after the image itself changes. That's where we use this SIFT. SIFT is generated like, there are a lot of strength, like they are invariant in the image scaling, they are partially invariant in the illumination changes also, they are robust to local geometric distortion as well. So a lot of kind of advantages is SIFT having, and they actually kind of work in a process. So the first one is definitely that the scale space extreme detection. That means it begins by identifying the potential key points across the multiple scale, right? And then it is like try to key point localization. So once the key point localization is being done, they kind of do the orientation assignment. Basically in orientation assignment, each of these key points is assigned to some kind of consistent orientation to ensure the rotation invariance, and then the descriptor generation, and that's how they are kind of following. So basically SIFT is very, very good when you kind of trying to think about you have an image and then the data points may not actually change even after the image itself can change, or it can have some details and all, and that's the reason the SIFT has been a very cornerstone when we think about computer vision models. And then another one, as I said, that the histogram one, that is also very good, which is the HOG. And then comes the deep learning model, which is being called as a CNN. So before we go to the CNN, if you will look into the HOG, that's also another important method. They are being called as a histogram of oriented gradients. This technique is widely used for detecting shapes and objects in any kind of images. And generally HOG, how they do is that HOG captures the local shape of the information by analyzing the gradient pattern across the images. And it starts by computing gradient throughout the image to highlight the edges. And this process is very stable as well. They are very powerful feature descriptor, or they are very powerful tools and ideal for the object detection and recognition in any kind of image. Then if you the another one is the deep learning method, as we know that. So now if you will kind of move to deep learning, that the CNN is one of the automatically very important one. They automatically learn from the hierarchical representation of the images, and there are a lot of ways we can do that. There are early layers, there are middle layers, there are deep layers, right? That's how we can do that. Early layers, they detect the basic features we have seen yesterday, such as age, color, feature, texture, those things. Whereas in the middle layer, they kind of combine this into a larger shape or the larger pattern. And the deeper layer, what they do is they capture the high-level complex objects and contextual relationships, right? And this hierarchical learning actually allows the CNN to outperform and handcrafted methods in many of the missions or tasks. And then another important one is the transfer learning, right? So transfer learning is actually another advantages of CNN is transfer learning, right? We can use the pre-trained network, trained of the massive data sets like ImageNet is something like that, and apply their learned features to our own task. So that's where we can use the transfer learning. So now if you will, as we know that CNN don't just learn from the features randomly, they build them up and gradually over the simple to the complex learning process. So as we said, there can be two processes using this feature hierarchical resolution. So the first one is the early layer. So these layers act as an age detector. They pick up the simple visual elements such as shape, edges, corners, textures, and those things. And then comes the middle layer of this CNN. So what middle layer do, as we said, that as we move from deeper into the network, this layer start combining the simple elements into the complex pattern, basic shapes, and those things. And then last comes the deeper layer, as we said that. At the deepest level, the network recognizes the whole object. They see the object and abstract the feature. For instance, if you can think about, it might identify a car or the face or a cat from the combination of the earlier learned patterns. And now if you will try to look into the statistical method, so statistical method is also providing a very different approach compared to the traditional as well as the deep learning method. Statistical method actually extract both global as well as the local patterns from images, enabling the image analysis and interpretation, right? They focus on the pattern, they focus on the distribution and texture rather than just learning directly from the raw picture. So there are some key techniques of this kind of statistical histogram. One is the color histogram, as we said, that it kind of represents the distribution of color. Then there is a GCLM, which has been also called as an texture analysis. So basically GCLM is that using the gray level co-occurrence matrices, they kind of capture the repeated patterns and surface characteristics. And then there are several other methods like age detection method or choosing the right method. That means choosing a right statistical method depends on several factors as well, right? Specific requirement of the task we know, available computation resources, need of the interpretability, and then also the understanding of the whole model, right? And the characteristics of the understanding of the data set. Those are the very important parameters when we try to select some kind of statistical methods. So as we said that now we have seen that how the statistical method works, and then another one is that we have seen all of this for the image feature extraction, right? Now we are moving into the audio feature extraction. We have seen there can be three types, right? The first one is image, then the second one is audio. So the audio feature extraction is that it also can be taught to understand the sound the way we the human do. So when we process speech or sound, our ears naturally actually breaks it down into the frequencies and patterns we know, right? So MEL frequency is another one of that. So MEL is also been called as an MFCC. So basically it's MEL frequency capture coefficient. Okay. So what MFCs does is that they do something very similar for the computers. Okay. So MFCs are very spectral audio features. They're designed to capture the most important part of the sound, and especially the frequencies of the humans are more sensitive to. Okay. And you can think of that MFC is a way of translating the raw audio into a language that computer can understand but still aligns with the human process. Okay? So basically this process starts by breaking the audio signals into small chunks and typically 20 to 40 milliseconds of long. And for each of this chunk we can actually apply some kind of mathematical transformation that can convert those kind of raw sound waves into the frequency component so that the machine can understand. And then instead of just treating all frequencies equally, what this MFC does is that use something called MEL scale. Okay, so which can be denoted by this. Okay, the MEL scale can be denoted by this, and MEL scale is basically and this equation is being called as an MEL transformation. Okay, so you will see that the frequency spectrum is the way that reflects the human sensitivity, and this formula, if you will use this MEL transformation, they actually compress the frequency spectrum in a way that, or in a reflection that as a human or the human hearing they are sensitive to. So by using this kind of transformation, we are not just processing the sound, we are also modeling the human perception. You can have to understand that these models are just not creating the sound, but they are also creating something which is sensitive to human ears. Right? That's why it is becoming more and more efficient. And then, as I said that definitely MFCs are there. So if we will try to go back and try to look into this understanding the transformation, you will understand that how this is being used. This formula is actually being used to convert the sound frequencies into the MEL scale. And while it may look like a little bit complex, you can see that all of these are doing as a mapping the frequencies in a way that mirror how as a human we can hear the sound. So they have varieties of definitely applications, like MFC forms foundation of modern voice recognition system. So when you speak to phone of the virtual assistant, right, that's very likely where we use this MFC to process your voice, right. These coefficients can capture the unique characteristics of each of the person's voice. Like you can also speak with the same agent, but then these MFCs will kind of try to capture each of the person's voice recognition, making them very invaluable for speaker identification and authentication system, right. So MFCs, as I said, that they can also reveal some subtle changes in the pitch. They can also kind of catch the tone, the speaking rate. All of these things, the small details, they can actually catch and put into their system or their model, right? So now if you will try to move into the time series features, so those are we have seen image, those we have just we have seen image, we have seen, now we will, the third one is that the time series feature extraction. So basically time series feature extraction is very crucial, right, when we are working with the data that evolves or that over the time period, such as like financial data, sensor reading, or weather measurement. So those are the things always change over the period of the time, right? And that's the period when we need to use the time series extraction. So while the static data sets, time series data carries the temporal information, right? That means pattern, trend, seasonality, and that changes over the period of the time. So by extracting the very meaningful features, we can actually run the raw continuous time signals into a structure inside that the models can interpret, the machine learning models can interpret, the machine learning models can use effectively. There are several major approaches for extracting the features from the time series, and I have tried to divide into the three divisions. The first one is the frequency analysis. So techniques like Fourier transformation or wavelet, they kind of help to decompose the signal into the frequency component, right? They reveal the hidden periodic pattern, and this is very useful for identifying the cyclic behavior such as like seasonal pattern in a cell, or decoding some kind of sensor signal. Where do we use it? This kind of frequency analysis. And then there is another one which is the statistical features, right? So here we kind of compute the matrices such as mean, variance, rolling statistics, and trend component to capture the changes over the period of the time. This is very simple method. This is very powerful, because it actually kind of try to measure the summarize the dynamics of the time series and help to identify the needs of the algorithm or the trends of the anomaly, right? And then as we said that the application, so with the extended features we can power tasks such as financial forecasting, anomaly detection, sensor data. So that is actually making our model more predictive, that is kind of making our model more reliable. So you can see that by using this frequency as well as the statistical techniques together, we can actually transform the raw data or raw time series data into a very compact, informative information. Now if you will will see the time series features, there are, as we said, there are several ways we can do that. First one, we all know about it, I think, is the Fourier transformation, right? Fourier transformation is nothing but one of the most widely used technique in the time series analysis. So it decomposes the time series data into a frequency component, right? Revealing the hidden periodic or cylindrical patterns that is not obvious in the time domain, right? So mathematically, this is expressed using this formula here, and which represents how a signal can be transformed from the time domain into the frequency domain. In simpler terms, it is like taking a complex sound and splitting into the individual notes, so you can actually use the underlying pattern. Similar way, there is another one which is the statistical method. So there are, if you go back here, there is a Fourier transformation. Then if you will look into the second one, which is the statistical method. So they actually, while Fourier analysis is focused on frequency, statistical method, they capture the temporal characteristics like for the data. So common features, they include the moving averages or standard deviation, some way like train components, which helps to describe how the data change over the period of the time. So now you will try to also sometimes see that together these features provide a very complete picture of both periodic behavior as well as the time-based behavior, right? And as I said, that there are like a lot of applications, real-life applications for this kind of methods. One can be the financial forecasting, then understanding the pattern in the stock market, or understanding the industrial monitoring, like detecting equipment anomalies, or by analyzing the data, you can understand the pattern over the period of the time. So there are several kind of real life advantages or real life applications for this kind of methods. And as we said that if you will try to look into some of the commonly used tools, we say that for the feature extraction. So for the image processing, these are the three: OpenCV, scikit-image, and TensorFlow. Whereas the audio, so if you will try to see the OpenCV, let's talk about one at a time. So the first one is the image processing, where we are looking into the OpenCV. So they actually provide a vast set of tools for image and video analysis, and they include feature detection, feature information, those kind of things, right? Whereas if you look into the second one, which is the scikit-image, so they are basically a Python library. We can use it in our daily basis. They built on top of SciPy, if you have heard about that. That makes it easy to implement the common image processing algorithm. Then another one is TensorFlow. I think all of us must have used the TensorFlow. This is actually more than just a deep learning library. It also allows us to extract and manipulate the features from images, like from some kind of using some pre-trained data or pre-trained model. And they are like, if all of these are very highly optimized, they are widely used in computer vision. We all know, like object detection, segmentation, image classification. We do use this kind of image processing tools quite a lot, right? Now there is another one, which is the audio processing. Here also we have like several popular libraries we can use. One is the librosa. There is a very go-to library for audio and music analysis, perfect for extracting MMCCs and other special features also. Then there is a Pi audio analysis as well. They also provide a very comprehensive set of tools of audio classification and feature extraction. Then another famous library is Soundfile. They actually kind of helps with reading and writing the audio files efficiently. So you will see most of these are kind of audio files and other libraries which have been used for several cases. And then another one is the time series. So it's like for the time series we have TS-Fresh, like quite common, which is automatically extract the exact hundreds of features from the time series datasets, right? Whereas the feature tool is also something very, very famous. It's the backbone of the data analysis in Python. We all know if you use Python, which supports the rolling statistics and trend the extraction and many more. It has a lot of actually advantages, right? And then there is also pandas, the kind of backbone of the analysis as well. They kind of also been used quite a lot. And then if you will try to construct the neural network entirely from scratch, it can be a great learning exercise. As I said, it helps to programmers to deeply understand that concepts and small building blocks of neural networks. However, if you try to kind of build them from the scratch, it is also very, very time consuming, right? And it requires a lot of effort. So you will see that to make a deep learning very easier and make a deep learning very faster, there are a number of libraries and tools which are available in the market. Today, you can just use one of those and create any kind of powerful neural network rather than just creating everything from the scratch, right? And then there are, as we said, that there are a lot of frameworks. So one of those are TensorFlow, there are Keras, there are PyTorch, right? So there are many of those. So if you will look into the one of those, which is the PyTorch, they are actually become extremely popular, right? I think most of our use it Python. Particularly in academic and research environment, we do PyTorch quite a lot because it's very valued for their flexibility, intuitive syntax, and their dynamic computation and graphs. So which makes our experimentations much more easier, right? So while it may not be as strong as visualization tools, compared to some of the other framework, but this kind of the PyTorch actually kind of gives you very compact, very fast performance, and relatively very simpler GPU installation for deep neural network model. So you can see that this is very kind of user friendly. First, there is another one which is the TensorFlow and the Keras. So basically, TensorFlow is an end-to-end open source platform. I think this is also something if you are kind of working with machine learning, must have used it quite a lot. This is actually been developed to help us to build and deploy machine learning model at a scale. So one of the key strengths of this is their visualization capability. It's very good into that, right? TensorBoard is a dashboard, for example, if you think about, gives the developer a very powerful and interactive way to visualize, to analyze and interpret the model, training process and results. And as we said, like the TensorFlow, there is another one which is the Keras library. That is also one of the high level, API which sits with the top of the TensorFlow, right? It's designed to be very user friendly and modular, and it also helps us to build deep learning models very faster and much simpler with the coding. So because of these ideas, while still having the scalability and power of the TensorFlow underneath, together this is actually kind of help us as an engineer, as a developer, the best of the world. That means you can use some kind, so you don't need to make any kind of machine learning or deep learning model from the scratch. By using this kind of library, you will be having quite a lot of help. From top of this, you can actually build up what you need in your model, right? So among these three, how many of this you have used? Any one of you have used any one of this? Yeah. Anyone else?
Now Jax is more famous than
Yeah.
Julia.
Yes, absolutely. Yeah. Anyone else? You must have heard about all these tools, right? Have you used any one of this? All of this you have used? Amazing. Yeah, I mean, if you kind of work with machine learning models, you must be aware of all of this. And these are, I think I have tried to show one of the simplest one, but there are a lot of advanced one as well in the in the monitoring system or any of this machine learning model. But this is a very common one and the easiest and the simplest one. We will definitely do a tutorial also using one of this. But as I said yesterday, it's a very good idea, at least if you kind of know the PyTorch or the TensorFlow. If you don't know that, after maybe the lecture, you can go back and have a look into that how does it work with the CNN or any kind of neural network. Then it will be easy for to kind of go ahead today with the tutorial, right? So as we said that as we know our infrastructure ages, it becomes more difficult and costly to maintain, right? So using traditional methods, that's the reason we kind of use the AI powered visual monitoring system, right? Because it provides a very smarter, more scalable solutions. And this artificial intelligence to detect very structural and environmental issues in the real-time method. So as we say that there are key parts of this approach in harnessing this AI for surveillance, for drones and for smart poles, right? And some of the issues this system can detect which there are 5 important ones. One is the crack of the surface of the deformation on the roads or bridges. Then the street light failure or any kind of inconsistent brightness level or any kind of obstruction such as fallen trees and those things. And then safety hazards like uncovered trenches and those kind of things. So unlike traditional periodic inspections, you will see that this AI-empowered video system, they operate continuously across both urban as well as rural environments. So the key benefit is definitely their immediacy. That means issues are flagged instantly, right, without waiting for the scheduled maintenance. And that's where actually, especially when you talk about the real-time detection in especially very valuable high-traffic zone, a critical infrastructure area, so which can actually significantly respond or reduce the response of the time and the safety. So that's the reason where we kind of try to use this. So continuing on from the previous one, so then there is another approach is not only about enhancing the infrastructure as we say, but significantly also improve the construction safety. So by identifying the hazards remotely, the field workers can actually focus on highest priority areas or highest priority repairs rather than just performing the broad-based inspection. That's where also, how do we use the system to actually work. At the heart of this visual monitoring system is basically to convert the raw video footage into the structured decisionary data. And how does it actually work? There is a steps to kind of do that. First is that the data capture. So basically camera, whether the fixed or the drone mounted is there, right? So they record the high resolution video across the key areas, like whatever areas you are interested. It can be highways, it can be beach, it can be any kind of utility zone, whatever your interest is. And the next step is the AI analytics. So basically the video then feeds the analyzed by the AI model that's been trained on the construction specific data sets. That means this model then use the real-time interface to detect the irregularities such as material fatigue or system automatically assigns to its severity score, right? And then the next step is that automated flagging. So once the anomaly is being detected, the system automatically assigns its severity score, right? And that is logged into the time stamp and location and flags it for the review. So then the next step is alerts, right? That means finally detected issues are sent to the dashboard or integrated into multiple work order system to take the final maintenance, right? Or the field inspection automatically, and that's how generally kind of methods work. There's a 4 basic generic processes, and then definitely there can be some sub processes also. But these are the main 4 processes that kind of make the system truly powerful to kind of understanding and learn the adopt over the time, right? Then as I said, there are a lot of key benefits of the AI in the infrastructure monitoring. So if you try to adopt the AI powered visual monitoring, does not just modernize how public agencies monitor the asset, it also actually transforms the entire process of infrastructure management. And how we can do that? By leveraging the power of AI in construction, municipalities, utilities, infrastructure. So actually being a consultant, you can gain an access to a range of measurable outputs or measurable benefits that support both day-to-day operations as well as long-term strategic planning. And among those, one is that timely repair, right? So as I said, one of the significant advantage is the timely repair. That means the ability to identify the issues before they become a crisis. So with the real-time video analytics, public work departments can instantly detect the problems such as we said, surface crack, light malfunction, or some structural shifts of the movement they could possibly occur. So instead of just discovering them weeks later during the routine check, right? This AI-driven approach, they kind of to predictive maintenance, they reduce the downtime. They mitigate the public complaints. They kind of avoid the costly emergency repair as well. So there is a lot of faster detection means the faster responses, right? Another benefit is that the cost saving. So cost saving is also another kind of very good benefit when you think about AI in the infrastructure. So maintenance budgets are often under pressure, especially when unexpected failures occur that require a large scale and expensive repairs. So by shifting from a reactive approach to a proactive one. So AI powered system actually help the agencies to extend the lifespan of the infrastructure and the assets of the prevent the small issues. So if you think about how they could reduce unnecessary expenditure, right, and they can focus on the resources strategically. So AI is actually kind of helping you to ensure the maintenance budgets, they can kind of go further. That also helps us to both operational efficiency, they can also help into the public service quality, right? And then another important or another key benefit is that safety enhancement. Right? That's one of the public safety is a very cornerstone of any kind of infrastructure plan, and AI plays a very important and very vital role in reinforcing this. So by integrating the AI into construction safety and maintenance, we add the critical layer of the protection for both public as well as the worker. So there are several ways we can do that, like dangerous cracks or sinkholes, in the walkways or roads, we can identify that. Failing structures that could collapse under any high traffic or any kind of storms, or debris or obstruction that put the drivers or the pedestrians under risk. There are several ways we can actually do that, and beyond, you can see that beyond the improving the safety in the built environment, this is actually also protect the field personnel, right? So because of, if you can think about the drone equipped with the visual AI, they can actually do this survey of the stalled bridges or any kind of roadside slopes or any kind of other hazardous areas, so that to understand before anything happens, before the inspection happens, they can identify the unsafe zone and they can take the measurement accordingly. And that actually kind of result in fewer accidents precise intervention and stronger public trust, right, towards the municipality or towards the city infrastructure program. That builds this process. And then another important one, on another, the key benefit is that the operational efficiency. So that's also kind of can be actually kind of done by using this AI in the infrastructure monitoring. So modern infrastructure, they oversight the demands of the smart workers, or they demand the smart workflows, right? So by using this kind of AI-powered visual monitoring techniques, we can actually gain a lot of data-driven decision making by capabilities which have the transform how they plan, right? How they prioritize and how they execute the maintenance list. Traditionally, there are field teams, they are being deployed based on the static schedules or reactive ticketing system. But now, by using this kind of AI agencies, we can actually rely on the real-time alerts rather than just the teams to go and visit them on a scheduled period of time. So, by using these AI agencies, we can actually rely on the alert systems to generate the dynamic tasks, right? Automatically sorted by severity and location of the risk. So, you can understand that what risks are there and what is the level of the risk, right? So you will see that that's nowadays very, very important for all of these kind of projects. You have to define the level of the risk and the task kind of being associated with that and how to mitigate that risk. Right? So those are the things can actually be flagged out very, very easily. This kind of operational intelligence actually improve also the workforce productivity, and then they also reduce the unnecessary site visits also can be reduced with that, and they also allow agencies to meet the performance goals like with fewer resources. So you can see that in essence of this AI transform maintenance from a reactive process into the proactive one, efficient systems that can actually maximize the impact with minimizing the effect. And now if you will try to look into the implementation scenario, one of the one is, as we said, the drone footage for highway crash detection, right? So if you will try to look into that kind of real world implementation of this AI infrastructure, you can see that while AI is in construction might sound futuristic, definitely, right? It's already being actively deployed today. Across the city streets or bridges or highways, you can see that AI systems are delivering a very measurable results. For instance, if you think about California Department of Transportation, which is also being called as CalTrans, they actually, on day-to-day basis, they have actually piloted the drone-based AI inspection to monitor these conditions in most of those California zone and most of the road surfaces across the vast highway network. This approach has dramatically reduced the manual inspection for them, and also they kind of improved a lot of maintenance prioritization over the area, right? So that they have actually kind of used it on a day-to-day basis. And now if you will try to look into the highway span autonomous, you can also see that there are a lot of processes that can be time-consuming or that can be risky. But by using this AI application in construction, drone equipped with high-resolution cameras or AI-powered visual detail imagery, they can actually be quite safe. They can save the time. They can also kind of analyze the computer visions. So there are certain things which they can actually measure. As you said, they can measure the surface crack. They can also measure the rutting or the potholes as well. They can also kind of measure some kind of joint failures. They can measure some kind of age wear. So there are a lot of other kind of anomalies are there which they can actually measure. So each of these anomalies is actually geo-targeted or geo-timestamped and categorized by their severity. So they actually help the engineers or help the team to understand and help them to actually take the decision and allow the maintenance team to prioritize the repairs, which is important according to their risk, and then respond the cycle, and that can actually enhance the asset of the life cycle planning across the city or across the country, right? And that actually makes us our infrastructure more resilient. That actually makes us our infrastructure much more cost effective. So as I said that then there are another implementation or another features is like the smart poles detect the light outage, as we said that. So urban areas increasingly depend on the smart infrastructure, particularly street lights embedded with sensor. I think especially if you will go in some of the smart cities, they are being used quite a lot, and that is being used because to get the better connectivity, to train the AI model, to enhance the urban intelligence. So these smart poles are actually can monitor their functionality. They can instantly detect where the bulb actually fails or when the power drops below the optimum level. So that's the AI-powered visual monitoring system we use, and these systems can visually verify lighting outage. They can set immediate actions to the engineers or the alerts to the central performance that this is the time that when you especially kind of need to take some action, depending on the risk as well. Depending on the area, it is not working. So as we know that this actually helps to kind of faster repair, the kind of improve the nighttime visibility, right, that will enhance both safety and accessibility, especially in some kind of regions where it is a big concern, right. We also reduce the risks as well of crime or accidents, right. That actually is one of the very important factors that this kind of AI-based street light embedded sensors are being used quite a lot in lot of urban as well as rural areas nowadays. So basically this capability is especially valuable in high density urban corridors or critical pedestrian zones where the good lighting is very important because of our safety or the mobility or to avoid any kind of accident. And then another one is the real-time alert which has been sent to the municipal work for the order system. So that is also one of the most transformative benefits by adopting this kind of AI for predictive maintenance, and that has the ability to directly integrate the detections with the city operation platform. For example, when you think about AI model that can identify a sidewalk hazard or that can identify a breach fracture with the city operation perform or maybe some kind of storm water blockage, right? They can automatically take an action. And how we can do that? By generating a work order instantly, right? Or we can assign the issue to the immediately right department to the field. So the AI model will be knowing directly which department to immediately contact or raise the concern, or tracking the progress of detection through the resolution, right? So this integration actually creates again the very seamless pipeline for surveillance of action. They kind of, instead of just relying on the manual reporting or delaying, they can actually automatically flag the issue, take the actions immediately, contact the right team, monitor their resolution over the real period of time, right? So you will see that by connecting with the city's existing operational infrastructure, they can actually kind of observe the problem very fast, respond them intelligently, make our infrastructure very sustainable in a way, resilient in a way. So that's how it generally works. And then another and the very last, or I would say the important one, is that the customizable alerts for the different asset types. So every city has their unique mix of infrastructure, like depending on every city, every country, like bridge, tunnel, even city to city also it can vary, not only the country, right? Even from bridges to tunnels to the retaining wall, electric substation, utility values, buildings, everything can vary from building to building, from city to city, depending on the what zone the city actually lies, right? So because of each of these assets, they experience different states, they experience different risks, they depend on the zone they are currently on. So what AI system can do is that AI system can actually tailor to monitor them individually. They can learn their normal wear pattern and identifying the early warning signs specific to each of these types, right? For example, AI system can be used for monitoring the expansion joints on the bridge, right, to detect the stress induced by wrapping before it becomes a dangerous one. Or watching the traffic signals. I think as a transportation engineer, people do use quite a lot for any kind of abnormal blinking pattern that could indicate immediate failure, right? And then scanning for storm drains during any rainy seasons, like to identify any kind of potential flood risk or any kind of blockage of the of the roads. Those kind of things can also be taken care of. So you can see that this level of customization and automation actually would be most impossible to achieve without manual oversight alone. You cannot just do that without manual oversight, right? You need to have an AI-enabled city infrastructure to manage this, to move on to one-size-fits-all approach, to assess the specific monitoring, and to making the intervention more targeted, more timely, and more cost-efficient, to make our infrastructure more sustainable, right? Anyone has any doubts till now? No? Okay, then let's take one or two quizzes here to understand the thing. So, which of the following best describe the physics-informed deep learning in SHA? It ignores the physics and only uses a data-driven model. B, right? It integrates the structural mechanics equation within the machine learning. That's the reason that it integrates that. Does the B is the correct answer? Anyone is saying D? Right? Yeah, so how about this one? In AI-powered visual monitoring system, what is the main benefit of the real-time anomaly detection? B, right? Because it enables the immediate alerts and proactive the maintenance actions, right? So now with this, I think we will end this lecture. But before that, I will also say that we have talked about a lot of deep learning methods. But I will also say to go back and try to look into some tactical tips or the strength of the weakness to kind of use the reinforcement learning models in the AI inspired infrastructure or the future what we have discussed today. So we discussed a lot of RFs and the little bit of deep neural network in last few lectures. So now if you kind of think of those reinforcement learning model and try to use one of those in the AI for infrastructure which we have talked that how AI could possibly change or bring the changes in the model. So if you think about those reinforcement learning model and can try to use in one of the particular cases which we have discussed today. So think about that and try to see how it could possibly fit into. So as we said that we have today talked about this transform maintenance, we have talked about the feature extraction, we have talked about real-time decision making as well, and then the key benefits of the timely repair, key benefits of the cost saving, and why we are interested about the operational efficiency as well, and then how we could possibly implement this scenario by using the drone, the drone inspection. We can kind of smart pole detection or those kind of ways that how the implementation scenarios can actually benefit when we talk about this AI-inspired infrastructure. And as I said that this is all the references which we have followed for this lectures. And if you are interested into any one of this, then I think you can go ahead with this to kind of see the further details of what we have discussed today to understand, to get into more details which we may not cover in today's lecture, right? So if you don't have anything else to ask, then we will end the lecture today and I will see you all for the tutorial. Yeah, thanks. I think thanks Manish. I think this is just now CR. B is the correct answer. So except that, do you have any further questions here? Okay, if not, then thank you everybody for joining online. I think I will see you all for the tutorial. So how many of you are actually comfortable with using MATLAB and Python? Who is actually using Python? You and you. All of you are using Python? Then how it will happen was I am going to use MATLAB. Anyone using MATLAB? You both are using MATLAB, but the functions are not installed in your MATLAB. So when you use that, I think now is it working the one when I say?
They are working using the online student button.
Okay, so the functions were actually not in that. So you have to install the functions, then only it will run. So if you, so from which university you are? Can't you just download their version?
I have done
So you are using the online student version? Yeah, that has a lot of limitations actually. Yeah, then thank you everyone. I will see you all the second half.
I can